Hello there. Today I'm going to show you how to integrate using spherical coordinates. Okay, I've got a couple applets here. I'm going to send you these links. One of them is just for spherical coordinates, and I showed you that the other day. And the other one shows you where the formula comes from for changing for integrating in spherical coordinates. And I'll show you that in a minute. Now, in this class, we're probably going to only integrate over one kind of set in spherical coordinates, and that's a spherical box. That's a set where rho, theta, and phi all go between two constants. So we'll learn how to integrate over a set of the form rho, theta, phi, where rho goes from A to B. Theta goes from alpha to beta. And what are some good letters for phi? Well, I'll just say from gamma 1 to gamma 2. I don't know that many Greek letters. So what does such a set look like? Okay, so this is like a box. That's terrible. Let's try that again. And suppose we have a function defined on E, and we want to integrate over it. But we can do this using an iterated integral. Now, it doesn't matter what order I write the limits in because they're all constants, but it's probably a good idea always to do it this in the same order when that happens. And I like to have rho on the inside, because you might do a problem once in a while where rho is not a constant. So the integrand, we're going to have the function, of course. But we can't just integrate the function over like that. We're going to need something, a volume factor there, just like we did with cylindrical coordinates. And we needed the extra r in polar coordinates for those double integrals. And unfortunately, this one, the one we need, is kind of complicated and hard to remember. It's one of the few things in this class that you have to remember, and that is not super easy to remember. Well, let me tell you what it is and then justify it. Okay, so that volume factor is rho squared sine phi. Now I'll justify it. So as usual, we'll cut the spherical box into little pieces, into little spherical sub boxes. And I'll call it a typical box EIJK. This is in any calculus textbook, and also I'll show you an applet with some explanation too. Okay, so the big box is E, and in each little box we pick a sample point, and as usual we'll call that rho IJK star, theta IJK star, phi IJK star. So we sample the function at each sample point, multiply by the volume of EIJK, and add up those sums and take the limit as the subdivision gets smaller and smaller. So take f of rho IJK star, theta IJK star, phi IJK star times the volume of EIJK. And we add all them up from I equals 1 to L, J equals 1 to M, K equals 1 to N. Take the limit of that as L, M, and N all go to infinity. So thinking of this as a mass, to find the mass of this object, we cut it into little pieces, estimate the mass of each piece by the density at one point over its volume. And if the deltas are small, then the density is approximately constant. So as we let the deltas go to zero, the limit approaches the actual mass. Now I just said deltas. The deltas are the change in the variables. So we have delta rho, delta theta, and delta phi. Now the thing that makes this tricky is that not all the boxes have the same size. So as it might be pretty apparent that the boxes that are closer to the origin are going to be smaller than the ones that are farther away. But it's worse than that. The volume also depends on phi. So boxes that are closer to the z-axis will be smaller than boxes that are farther away. And so let's justify that. So let's find that the volume of one of those little boxes, or at least approximate it. We'll get a good enough approximation so that it works when we take the limit. I'm going to draw a picture similar to the one above. of one of those little boxes. I'll draw it big so that we can write other things. What EIJK. Now, if the deltas are small, then this is approximately a box. So the volume is approximately the product of the three dimensions. Now, one dimension is exactly delta rho. Another dimension is the length of that side there. Well, that's a circular arc, and if the central angle is delta phi, and the radius is rho, really rho IJK, but I'll just call it rho. And if the deltas are small, then that circular arc is real close to a line segment. And the length of the line segment is about the same as the arc length. And by the arc length formula, the arc length is the central angle times the radius, which is rho delta phi. So another dimension of this box is rho delta phi. Now the remaining dimension is the trickiest one. Oop. Oop. Try again. Yeah. Okay, let's fix that a little bit. Okay. That is the length of this arc here. Because, and again, if the deltas are small, the arc is approximately a line segment. So that arc is part of a circle that wraps around the z-axis. And the central angle for that arc is theta, our old friend theta, from cylindrical coordinates and also spherical coordinates. What's the radius? The radius is our old friend r. Now, r is not a spherical coordinate, but remember we found out what r is the other day. Rho is r sine phi. So the remaining dimension of this little box is arc length times the central angle, which is rho sine phi delta theta. There's a typo there. That should be a phi, not a theta. Okay. rho sine phi delta delta theta. And that the volume of the box simplifies to rho squared, rho squared sine phi delta rho delta phi delta theta. So in this triple sum, we can replace the volume of EIJK with that expression, and the limit will be the same. We replace it with rho squared sine phi times the 3 deltas. And of course, I need the subscripts and the star. But so now we have a real triple Riemann sum. If you take the limit as Lm and then go to infinity, you get an iterated integral. So you get the magic formula there. So that's where it comes from. And now I'm going to show you an applet to maybe give you a better feeling for why this works. Okay. Okay, there it is. Yeah. Okay, so here we want to integrate a function over this kind of half cantaloupe shape. What the function is isn't so important here. The more important is the limits of integration and the region. Now this is a hollowed out sphere. The outer radius is 5 and the radius is 3, and z is always positive. Now on the right, it's been divided, subdivided into lots of little spherical boxes. And you can see they have different volumes. The ones farther from the origin are larger in area, volume, sorry. But they also get smaller near the pole, near the North Pole, and larger near the equator. Now the rho dimension of the boxes is always the same. It's always delta rho, but the other two dimensions change. The dimension along the latitude line changes. It's proportional to rho. And the one along the let's see. Yeah, and the dimension that goes along the longitude line changes. That one is also, it's proportional to rho. Now on the left is the 3 dimensions in rectangular space, and the volume of each box is just the product of the 3 deltas, and they're all the same. But when you use spherical coordinates, you're on the right in the real world, on this cantaloupe, they have different sizes. They have different volumes. And they have a justification for that, for the rho squared sine phi. It's different from the one we used. This is fancier. They use something that similar to what we're going to do later, using the Jacobian, but we'll see that later. Okay, so let's do an example of using this. Oops. Okay, so here's an example. Find the integral over the ball x squared plus y squared plus z squared less than or equal to 4 of square root of x squared plus y squared plus z squared. So I'll sketch the region. It is a ball. Ball means that it has everything inside. A sphere is a hollow surface. Okay, so I'll erase the hidden halves of those circles. Radius is 2. Okay, so let's find the limits of integration. Theta goes from 0 to 2 pi all the way around in a circle. Phi goes from 0 at the North Pole to pi at the South Pole, and rho goes from 0 to 2. Now, for the square root of x squared plus y squared plus z squared, don't do what Robin did. Okay, this is what Robin does. He replaces x, y, and z with their conversion formulas, and he starts to simplify it, and probably makes a mistake in simplifying it because it's tricky. What you should do is just use the idea that rho is the distance from the origin. That's from the distance formula. So the integrand is rho, and we also need that extra rho squared sine phi. We always need that in these spherical triple integrals and spherical. Now, once you've found the integral, the integration is easy. So I'm going to kind of blow through it. The inside integral turns out to be 4 sine phi. The next integral turns out to be 8. And when you integrate that constant, you get 8 pi. So that's the final answer. Now this answer makes sense because the integrand is positive, and we got to find a positive final answer. And I made a careless mistake there. I did everything right except for the easiest part, which is the last integral. So to integrate a constant, that's the constant times the length of the integral, which is 16 pi, not 8 pi. That's today's duh moment. Sorry about that. Okay. So I think this is enough for now. In the next video, I'll do some more examples. Bye.